Welcome back. So we left the discussion here where we're trying to establish some link between a orthogonal decomposition of a square matrix and a singular value decomposition of a non-square matrix. Okay, so we know that this guy is square, but this guy is not square, right? Okay. Now the thing is, this P doesn't have to be orthogonal, right? But U and V has to be orthogonal in the case of singular value decomposition. And so this guy D has eigenvalues and this guy sigma has singular values. In fact, as I mentioned earlier, I mean, you are expected to get a band of singular values sorted in a descending order. Now, question is, what are these guys? I mean, how do I know what these guys are? I mean, how do I use these guys? Because as it is, the matrix A is not a square matrix, right? But I mean, the transposes, taking transposes of matrices gives you some sort of an translational power. So let's do that. And we know that since A is not square, I mean, there are ways to make it square, right? I mean, we will see this technique revisited in regression later on and in other places, right? Okay. So A transpose. If I look at this, now if A is not square, I mean, let's say A is m by n, then A transpose is n by n. And so the A transpose becomes m by m, which is a square matrix, right? But in this case, what I know is my U, A is U sigma V transpose, and then A transpose is the transpose of that, right? I mean, if I take the transpose of that, what I'm going to get is V transpose transpose, sigma transpose, and U transpose, right? Please remember that U and V are orthogonal matrices, so that we will use this in a moment. Now, what will happen is, if I look at these two, V transpose transpose is nothing but V, right? Then you have V transpose, which is an identity matrix, right? And then you have this sigma, and then you have this sigma transpose, right? So then you have a U, and then the identity matrix with sigma and sigma transpose returns sigma sigma transpose, right? And then you have a U transpose. So see what we have done by taking transposes. We have changed the output of the new matrix, which is A transpose, right? The V is no longer here, V is gone. You see that, right? And you have both U and its transposes on the either side. So now, if I try to map this back to my original, diagonal decomposition of a matrix, you can see there is some similarity. What similarity do you observe? You see that there is this guy D, okay, which is a square matrix, and then there is this guy, and because it's a diagonal matrix, it has to be symmetric, right? Okay, what about this? Is this a symmetric matrix? Yes. So this guy is also a symmetric matrix, and because it's a symmetric matrix and supposedly with real values, its eigenvalues are real and distinct. Okay, all right. So we will use this, any symmetric real matrix, the eigenvalues are real and distinct, we'll use that. Okay, all right. Similarly, if I do an A transpose A, I will not repeat the calculation. If I do an A transpose A, you will get an n by n matrix, right? According to the structure, what you are going to get here is okay, all right. So what will happen here is, this guy is also a diagonal matrix. So you now start observing the similarities between the two decompositions, right? Okay, so this guy is also a diagonal matrix, okay, and these guys V transpose is the same, right? Here also U transpose, unlike the initial structure where you have a different matrix on the left and a different matrix on the right. Okay, so now if I have to compare, I mean, so what can I say? I mean, if I have to compare between V and P, let's say, so what does V has? V has eigenvectors of V has eigenvectors of A transpose A, and what does P has? P has eigenvectors of A. Okay, the D which you see over here, the D has eigenvalues of A, right? And this guy, sigma sigma transpose, right? Sigma sigma transpose has eigenvalues of A transpose A. Makes sense, right? Because A transpose A is a square matrix, so therefore it admits of eigenvalues, right? Okay, so therefore, I mean, the diagonal, the eigenvalues of A transpose A. So what we can say clearly is that I cannot see. Look, what was the original problem? The original problem was I cannot compute the eigenvalues of A. So I figured out a way, right? So instead of computing eigenvalues of A, I compute the eigenvalues of A transpose A. Okay, and what will that do? That will give me the singular values of A. This is what I was after, right? Remember, this is where the problem started. I mean, I wanted to compute the singular values of A because this A is the information matrix, and that information matrix, remember, if you recall, the information matrix has bunch of journals as the rows and a bunch of journal matrix as the columns. We did not want to, use a bunch of different features to rank the journal because it becomes confusing, right? Okay, so instead we wanted one value. So that one value is given by the singular values of A. I could not find the singular values of A directly, so instead what I did was I found the eigenvalues of A transpose A, and those are nothing but the singular values of A. Okay, all right. So if I give you a tiny weeny example without computing the singular value decomposition, it goes like this. Let's say I'll take a square matrix example. It's okay. So it's like 2 2 1 1. Okay, it's actually a low rank matrix. This matrix doesn't have full rank. As you can see, if you multiply the second row by 2 and subtract from the first row, the one row completely vanishes, so the rank becomes 1. So I mean, I need to have a full rank decomposition in order to have, this is supposed to give me 2 eigenvalues, right? But in this case it won't. So what will happen is, what I want to do, so this is a singular matrix. This matrix is a singular matrix. Singular in the sense, not singular in the sense of SVD, but singular in the sense that the determinant is 0, right? Okay. So what I can do is, I can do an SVD of this guy, and if I do an SVD, what I will obtain is that I'll get a U vector matrix, which is 2 1 minus 1 2 multiplied by this guy, and then on the right multiplied by the V matrix, which is nothing but 1 1 and 1 minus 1. All right. So what you can see is, like, if you look at the first column of this guy, so what is the magnitude of this first column? Is square root of 2 square plus 1, so it's like square root of 5, right? So square root of 5, which is like this is, you take this as U as one entry, and then multiply that with this guy, okay, and then you multiply that with the first row of the rightmost matrix, which is V, right, and the magnitude of this row is nothing but square root of 2. So you can consider the first column of the U matrix as U1 times the first singular value, which is sigma 1, in this case square root of 10, times the first row of the second matrix. Okay, so what happens is, what is U1? U1 is nothing but the first eigenvector of the matrix U. What is sigma 1? It's the first singular value of the sigma transpose. And what is V1? Is the first eigenvector of V, the matrix V. Okay, all right. Now, assuming that we have sorted out the eigenvalues in the descending order, as you can see clearly in this example, square root 10 is greater than 0. I mean, and therefore your band singular value band is this. Right, that's about it, because it's a 2 by 2 matrix. Okay, so the maximum information that you can gain lies along this direction. Which direction? Lies along this direction, u1 sigma 1 v1. Okay, so this guy contains the most information in the information matrix. Okay, and this matrix is a matrix of rank 1, so it's a low rank projection. Okay, so what is u1 then? I mean, u1 is some combination of input data, some combination of input data, and v1 is combination of some other input data, right, and sigma 1 is the singular value. Okay, so therefore if I rewrite this, I can easily say, in fact I can say, because the maximum information, because there are two components here, right? I mean, u1 sigma 1 v1 and then u2 sigma 2 v2. So there are two components. Among these two components, this guy contains the most information. So therefore, I can say that this is the first principal component of my information matrix. Okay, A. And the second one, u2 sigma 2 v2, is the second principal component of my information matrix A. Okay, all right. So therefore, what I can see is, from a singular value decomposition perspective, we move to PCA, which is principal component analysis, which in practice is also looking at design matrices or information matrices which are not square in nature, okay, and trying to figure out which are the most important components that we can keep and which are the sort of lesser important components that we can throw away. So in essence, what happens is, these are both SVD and PCA can be thought of as feature decomposition, feature reduction, dimensional reduction techniques. Okay, because one of the problems in machine learning is the curse of dimensionality. I really don't have problem with a lot of data, right? I do have problem with is a lot of noise, and if the noise is by mistake considered as signal, okay, as a feature. So if I have too many features, I have a problem, right? In the feature space, geometrically speaking, ideally speaking, actually a two feature problem. Data with two feature problem is ideal because I can visualize everything in two dimensional space and figure out the patterns, but that usually doesn't happen. Data is usually often multidimensional, and there are ways to handle multidimensional data, but even then the interpretation becomes difficult if the dimensions are out of control. Okay, so which is why people always look for ways to reduce the dimensionality in such a way that the noise gets filtered out, okay, and we retain as much information as we can. Okay, so with this, I think we should move to sort of principal component analysis. So I'll just before doing that, I'll present a summary. Okay, and the summary is this. We have an m by n matrix that is decomposed into three pieces, m by r, okay, sigma r by r, and v transpose n by r. All right. Typically the value of r is much lesser than m, so these r's are nothing but concepts that we learn. Okay. So in the context of the problem that we are discussing, what are the concepts? The concepts are probably the higher impact journals, mid impact journals, and low impact journals, right? So those are the three concepts that we learn from the journal data. Okay, and so that is nothing but the left singular vector. It's a left singular vector. Left singular vector. This one is the right singular vector. Okay, all right, and this guy are the singular values, and R is nothing but the rank of A. Okay, so basically what R is nothing but the strength of each concept. So as I said in the example that I just gave, right, I mean, or the problem that we solved, if it's a high impact factor journal, what's the strength of that concept? I mean, what's the strength of a low impact factor journal? Given that you have a lot of data, you probably could have, a lot of journals which are low impact factor and a few journals only which are high impact. That is exactly what we wanted. We actually wanted to filter out the information from the noise. So basically there's a lot of dump. I mean, there are a lot of really bad journals, right, and then there are few good journals, right? So the idea is to filter out that information from a slew of journals, and basically the matrix that we considered was I can give you an example now. I mean, like I can give you the real world example. That problem there are like 50,000 journals. So we had 50,000 journals to parse through, okay, and those were the number of rows of A. Okay, and we had about 23 features or dimensions. Okay, that were nothing but the number of columns of A. R is whatever. Okay, so I mean, we kind of pre-decided that R would be 4. Okay, all right, and clearly M is way greater than R, right, and R is also greater than N. Okay, all right, so this is what SVD is, and we also conjectured that PCA is a natural extension of SVD. Okay, so let's now move on to principal component analysis. I mean, what I'll try to do throughout the course of the lecture is try to give examples from computing mostly. Okay, and so the next example that we will give is principal component analysis. This is taken from Raj Jain, and I mean, in fact, he has a few years back he has written, a couple of decades back he has written a fantastic book on workload characterization, computer system performance analysis. Okay, and in the context of that, so basically what he wanted to see is that, look, I have some output, okay, and then there are two inputs. I mean, these inputs could be central processing unit, IO devices, RAM, etc., right? Okay, and the output is measured in terms of how much information I can process and how quickly I can process, right? So if I can write that as the output as a linear combination of the bunch of inputs, weighted linear combination of bunch of inputs, and from there can I figure out which ones are the most important? Okay, all right. So the problem is this: if you are able to write Y, your output, as a weighted combination of your inputs, right, then can you assign weights in such a way that the output provide a maximum dissemination and maximum discrimination along the components. Okay, so just like SVD, if you recall, in SVD we had that U1 sigma 1 V1, right, small u1 sigma 1 V1 and small u2 sigma 2 V2, right? Okay, so we have seen that among those two components, U1 sigma 1 V1 gave us the maximum discrimination along the component. Okay, so if that's the case, then I'll take, let's say in this case we have 2, like Y1, which is nothing but summation I is equal to 1 to 2 Wi xij, right? So what will Y1 be? Y1 be W1 x12, right, plus W2 x21, right? So these are the weighted combination. So you have two components, two input components to your output, right? Okay, and if the weighted combination, and similarly you can compute Y2, right, and let's say there are only two components, Y1 and Y2, we will see which one among the Y1 and Y2 give us the maximum discrimination, and that then we will call, let's say Y2 gives us the maximum discrimination, then Y2 becomes the principal component 1 and Y1 becomes the principal component 2 in such a way that if it so happens that the first principal component actually explains the maximum variance along the output, let's say 97%, 98%, then rest of the contribution of the other component doesn't really matter, right? So you can throw it away. So that way we reduce the dimensionality of the problem. Okay. All right. So typically, once again, we will leverage the ideas and concepts of linear algebra. Okay. So the idea is in this particular case, what we think of is the y's, like let's say in this case y1 and y2, they form an orthogonal set, which means their inner product has to be 0. Okay. Now, what does it mean? I mean, if you go back to the SVD lecture, I mean, you will see that if two vectors are orthogonal to each other, I mean, there is the likelihood that those guys are related or those guys are sort of similar is really low. I mean, it can't be, right? Okay. So that's a very powerful thing. I mean, exploiting the geometric orientation of two vectors to determine whether there exists any relationship between the two. Okay. All right. Okay. So using that, so the idea is this: given a matrix, of course, and the information matrix, we find the correlation matrix. Okay. Find the eigenvalues of the matrix and sort them out in the descending order, exactly the way we have done in SVD, if you recall, right? Okay. And then for each eigenvalue in the band of eigenvalues, you find out the corresponding eigenvectors, multiply it exactly in the way that you have done in SVD. Okay. And this will give you the required loadings or contributions. Okay. All right. So this is my data. Okay. All right. So the data is, I mean, you see there are data in two directions. One direction is the number of messages XS. Okay. This thing is like number of messages sent, and the second column is number of messages received. Okay. And then there are a bunch of values that are given. Okay. All right. One of the thing that we have done here is scaling. Okay. Now, why the scaling was required? Because if you observe the values along the columns of both number of messages sent and number of messages received, you will see there is a large deviation. Okay. So in order to kind of squeeze the deviation and normalize it, what we have done is we did a means normalization, which means that from every data point, you assuming that this follows the normal distribution, if from every data point, I mean, you compute, so first you compute the mean, which is something, and standard deviation. So from every data point you subtract the mean, divide it by the standard deviation. If you do that, okay, you will get values which are now, if you look at the normalized values of number of messages sent and number of messages received, you will see less deviation, much less deviation compared to the first column. Okay. And the idea is, if you do that, you will see the sum of the values along the column goes to 0. Some of the values along the column of received messages also goes to 0. Some of the squared values become smaller, and mean and standard deviation mean. So you basically, what you have done is, the data that is given to you, you centered it now around a mean 0 and a standard deviation 1. It's a normal distribution. Okay. All right. Okay. So we have done all that for both X and S. Okay. Compute the standard deviation, right? I mean, these are very simple process, right? I mean, the formula for standard deviation. So I'm going to go through these quickly. Now, we did that normalization, right? And then you compute the correlation. Okay, correlation between what? Correlation between, because we wanted to see that if there are two input values or input variables, number of messages sent and number of messages received, how strongly correlated they are, right? And using that correlation, basically you compute the correlation, prepare the correlation matrix. In the correlation matrix, what you see is very interesting, right? I mean, if you look at the correlation matrix, you see that the matrix is symmetric. Nice. It's 1 along the diagonal and 0.916 along the off diagonal. So if you take the transpose of it, nothing changes, right? Okay, beautiful. And it's also like all the values in the matrix are positive. All the values in the matrix are positive. So it's a real matrix. It's symmetric. Okay. Also, it's positive definite. Now, it's sort of easy to compute the eigenvalues and eigenvectors of this matrix because it's a 2 by 2, and we also know we will observe one thing. If you recall, in the SVD lecture I said that if a matrix is real and symmetric, the corresponding eigenvalues are distinct, and that has an implication. The corresponding eigenvalues are distinct. Okay, we'll cover that in the next lecture. Okay, the corresponding for now we are going to leverage that information, and we indeed see that's the case. The eigenvalues that you found are 1.916 and 0.084. These are real and distinct. Okay. And using these eigenvalues you compute the eigenvectors, and when you compute the eigenvectors, what you will observe is the corresponding eigenvectors will actually be orthogonal to each other, which indeed they are. Okay, I mean after length normalization, these are the corresponding eigenvectors which correspond to the eigenvalues 1 and 0.916, and you can see you take the inner product of q1 with q2, you will get 1 over square root of 2 1 over square root of 2 plus 1 over square root of 2 minus 1 over square root of 2. Basically this goes to 0. Okay. So what you now do is that because you are able to figure out the eigenvectors, you construct the matrix, and in the matrix, the columns of the matrix are the eigenvectors, correct? Okay. So now I obtain, so basically what was the idea? The idea is that you use the eigenvectors, okay, and you have the normalized variables xs and xr, and then you take a linear combination of these two and produce your output. Okay, we exactly do that, and what we find out is that the sum must be 0 and the sum of the squares will explain. Now let's look at this visualization. What do you see? There is this principal factor, let's say this is y1 along the horizontal axis and y2 along the vertical axis. Okay, so by using the formula that how much you are able to explain, right, okay, which is pretty simple, the first factor explains 95.7% of the variation in y, the second factor explains only 4.3. So what's the, I mean you don't need to be a rocket scientist to decide that the second factor has to be dropped. Also if you look in the visualization, you can see easily that along the direction of y1 from the mean you see the maximum variance. Along the vertical direction from the mean you actually see very little variance, right? Okay, so therefore you can easily drop it. Okay, I mean so we come to the end of PCA. However, we are not done with PCA because there are some important relations in PCA which are driven by linear algebra foundations, which I am going to talk about. Okay, and I am also going to talk a little bit about the eigenvalues and eigenvectors. Okay, so in the next lecture what we will do is we will exploit some of these relationships between eigenvalues, establish some of the relationships between eigenvalues and eigenvectors, and also we will talk about revisit some of the basic concepts in linear algebra. Okay, thank you so much, keep watching.